In this video we start a new topic, which is duality in linear programming. The concept of duality is one of the most important concepts in optimization in general and in linear programming in particular. It has an impact on different aspects of optimization, including theory, algorithms, and practical applications. And we'll go ahead and start with a motivational example illustrating how duality may arise in practice. In this example, we have a small manufacturer called Supercleats Incorporated that produces 4 models of soccer shoes named Dynamo, Spartacus, Torpedo, and Kenga. This table here provides the information on the price of each pair of shoes and then the different types of costs associated with the manufacturing process. Essentially, to produce a pair of Dynamo cleats, we need to spend $15 in material cost, $35 in labor cost, and $5 in overhead cost. And a pair of Dynamo sells for $100. Then we have similar information for the other types of shoes, Spartacus, Torpedo, and Kenga. And the last column represents the budget that we have for the material costs, labor costs, and overhead costs. And our objective is to utilize this budget in a way that we generate as much of the revenue as possible from selling these shoes. All right. There are a couple of additional constraints related to the demand on different types of shoes. More specifically, the demand for Dynamo and Spartacus shoes is limited to 1,000 pairs each. This is a typical production planning situation where we have 4 different products and we need to decide on the quantities of each product to produce in order to maximize the revenue. And we have 3 different types of resources. So we have the material costs, labor costs, and overhead costs. And in addition, there are a couple of demand constraints here that are essentially the upper bounds on a couple of variables. Okay, so this is how our LP model looks like. Nothing new here. But next, in addition to this small manufacturer, we are going to consider a bigger company, which is called All Shoes United, which wants to acquire the Supercleats. Alright, so they want to prepare an offer that would minimize ASU's annual expense to cover the Supercleats operations while making sure that the offer is attractive for the Supercleats Incorporated. And what's an attractive offer? The manager of ASU, named Don Carl Leon, wants to make sure that the offer they make is something that Supercleats can't refuse.
I'm going to make him an offer he can't refuse.
Which they assume is such an offer where the annual payments to Supercleats will be no less than the revenue they expect to generate per year. So why is it an offer that the Supercleats can't refuse? Because they're essentially getting their maximum possible revenue from ASU without a need to even sell the shoes. So it's really a good deal that is hard to pass on. Let's look now at the model that we have, and now we are gonna look at it from ASU's perspective, and we are trying to estimate how much money ASU will have to pay to the Supercleats so that their expenses on this acquisition are as low as possible. Alright, so to start with, assume that ASU doesn't have the complete information about this model. Of course, if they had the complete information about all the data that are used to generate this LP, they could have just solved the LP and find the optimal solution, right? And this would be the amount they would pay for the acquisition. So assume for now, though, that they only have the information that's available in the public domain. For example, you could get the information about the selling price of the shoes. You could go to the store and check it out, right? So you could see that Dynamo costs $100 per pair, Spartacus is $80 per pair, and so on. And also, being experts in shoe manufacturing, they could easily estimate the cost of materials required to produce each pair of shoes. So they could have gotten this data in the left-hand side of this first constraint easily, because remember the first constraint was the material cost constraint. And then assume that somehow they found out that the superclids spend $45,000 per year on materials, and then they'll have the objective and the first constraint of the model that the superclids have. Now, having just the objective and one of the constraints of the superclids, all shoes united can try to evaluate an upper bound on how much they'll have to pay for the acquisition. In fact, if they just solve this model with a single constraint, then the optimal objective for this small model will be at least as large as for the whole model, right? So because we drop several of the constraints, as a result, our feasible region is getting bigger and the objective can only get larger. So by solving this problem with just one constraint, all shoes united can get an upper bound on the amount they have to pay for the acquisition. Alright, so a model this simple is very easy to solve. In fact, we know from the simplex method that we'll only have one basic variable here, so there will be only one variable that will have a positive value. And it is clear that the variable that has the positive value has to be the variable that has the highest return here, meaning that we have the highest ratio of the coefficient in the objective to the coefficient in the constraint. If we look at the ratios for all the variables, we have 100 over 15, 80 over 10, 60 over 8, and 50 over 5. The highest one will be 10 for x4. So in the optimal solution, the variable x4 will be set to the maximum possible amount, making sure that we don't violate the upper bound here. So it's going to be 45,000 divided by 5, right? So and then we'll plug in that value in objective to obtain the optimal objective. But another way of getting that upper bound could be just multiplying the constraint here by this maximum ratio that we were looking at. 50 divided by 5 is 10. So now if I multiply the constraint by 10 on both sides, this is what I'm gonna get for this constraint. So it's gonna be equivalent to 150x1 plus 100x2 plus 80x3 plus 50x4. And all of this is less than or equal to 450,000. So now looking at the coefficients for all the variables in the objective and the left hand side of this constraint, we can see that the coefficients in the left hand side of the constraints are at least as large as the coefficient in the objective for every variable. So for example, for x1 we have 150 here and only 100 here, 100 versus 80 for x2, 80 versus 60 for x3, and for x4 the coefficients match, so they're both 50, right? And because of that we can say that our objective z is less than or equal to the left hand side of our constraint. Why? Because all the x's are non-negative and the coefficients for x's here are at least as large as they are here. Therefore, we get an upper bound on the objective by looking at the left-hand side of our constraint, and clearly the right-hand side of the constraint will give us an upper bound as well. So essentially we have z is less than or equal to the left-hand side, less than or equal to 450,000. Anyway, from this single constraint, we can get the upper bound on what we'll have to pay for the acquisition. So we can see that z will be less than or equal to 450,000. And this is our upper bound, right? But then we know that after we introduce these additional constraints that we didn't consider because we don't have information about them, the optimal objective of our model is going to decrease compared to what we have here. So it's going to go from 450,000 down to something more reasonable. So these 450,000 only give you an upper bound on what you will have to pay. Perhaps not a very good upper bound. So now, what if, let's say, we had not just the first constraint, but the second constraint as well? What if we add the second constraint to the mix here? And now if I had this model right here. So we could try to use the same argument here, and generally I could actually combine these two constraints. Say I could multiply the first one by y1, I could multiply the second one by y2, and I could sum up the resulting inequalities and try to use them to obtain an upper bound on my optimal objective for my original problem. So for the coefficient for x1, when I sum up the two constraints, I'll have 15 times y1 plus 35 times y2, right? I multiply 15 by y1, 35 by y2, and this will give me the coefficient for x1 in the sum. So that's the coefficient for x1. Then to compute the coefficient for x2, we have 10 times y1 plus 22 times y2. That's the coefficient for x2, and this is coming from here, right? The coefficient for x3 will be 8y1 plus 18y2, right? So we have this in this column right here. And finally, the coefficient for x4 would come from this column right here. We would have 5y1 plus 10y2 times x4. So this would be now our left-hand side of the combined constraint obtained from multiplying the first constraint by y1, the second one by y2, and summing them up. And this would be less than or equal to 45 thousandths times y1 plus 100 thousandths times y2. Alright, and now we can select any non-negative values for y1 and y2, and we need to select them in a way that will allow us to obtain an upper bound on the optimal objective for our problem, right? So I want z to be less than or equal to the left-hand side of this constraint, which is in its turn less than or equal to the right-hand side of this constraint, and therefore this will give me the upper bound on the objective z here. So in order to have this inequality right here, I need to make sure that the coefficients for each variable in the left-hand side of my combined constraint are at least as large as the corresponding coefficient for the same variable in the objective. So for example, for x1, I need to make sure that this coefficient is greater than or equal to 100. Then for x2, I need to make sure that my coefficient is greater than or equal to 80. For x3, it needs to be at least 60. And then for x4, it needs to be at least 50. Okay, so and now if I want to get as tight of the upper bound on the z value as possible, what I need to do, I need to minimize this function of y1 and y2 here, subject to these four constraints right here. So essentially we are going to obtain another LP, which will be to minimize 45 thousandths times y1 plus 100 thousandths times y2, subject to 15 times y1 plus 35 times y2 is greater than or equal to 100, 10 times y1 plus 22 times y2 is greater than or equal to 80, then 8 times y1 plus 18 times y2 is greater than or equal to 60, and 5 times y1 plus 10 times y2 is greater than or equal to 50. And all of the variables which are y1 and y2, of course, are non-negative. See, because when we have the non-negative multipliers, the sign of the inequality doesn't change, and as a result we will have a valid upper bound on our objective, and we minimize because we want to minimize our expense, right? So we want to get as tight of the upper bound on the quantity that we'll have to pay as possible, all right? And actually this was done using just these two constraints, right? But assuming we had all the constraints available, we could extend this logic to all the constraints, but we could look at this model from a different perspective, from the perspective of all Shoes United who want to minimize the cost of acquisition. And for that, they would write the following model. So extending our logic to all the data, we would have the following multipliers. We would have the multiplier of y1 for the first constraint, y2 for the second, y3 for the third, y4 for the fourth, and y5 for the fifth. So we have 5 of these multipliers, right? And we need to find an optimal combination of these multipliers such that we can use the right-hand sides of the inequalities to obtain an upper bound on z, which would be as tight as possible. And extending our logic that we used for just 2 constraints, what we need to do, we need to make sure that when we sum up the coefficients for x1 multiplied by the corresponding values of yi's in each constraint, then that sum should be greater than or equal to 100, right? So then when we look at the column for x2, the same thing should be true. So when we multiply 10 by y1 plus 22 times y2 plus 5 times y3 plus 1 times y5, that sum should be greater than or equal to 80, and so on. So you'll have 4 of these constraints, right? And we can write down the following LP from the all shoes united perspective. So you'll have minimize 45 thousandths times y1 plus 100 thousandths times y2 plus 20 thousandths times y3, then plus 1000 y4, and plus 1000 y5. So this is our objective when we try to minimize this upper bound. And the constraints would be, we need to ensure that we dominate the coefficients in the objective. So it will be 15 times y1 plus 35 times y2 plus 5 y3 plus y4 is greater than or equal to 100. So then for the second column we'll have 10 times y1 plus 22 times y2 plus 5 times y3. Then we have 0 y4 and 1 y5. Is greater than or equal to 80, so we need to dominate the coefficient for x2. Then to dominate the coefficient for x3, we will have 8 times y1 plus 18 times y2 plus 4y3. Then we have zeros for y4 and y5, and this is greater than or equal to 60. And the last constraint would be for x4, we will have 5y1 plus 10y2 plus 4y3 is greater than or equal to 50. And all the variables y1, y2, y3, y4, y5 are greater than or equal to 0. Alright, so we obtained a different LP here, which is essentially approaching the same data that we had for a small manufacturer from a bigger manufacturer's perspective that wants to acquire this smaller manufacturer. The smaller manufacturer is trying to maximize its revenue, while the bigger manufacturer is trying to minimize its cost of acquisition of the smaller manufacturer. So we can see the way we use the data from the model that we have here in the other model is the right-hand sides from the original LP became the coefficients for the variables in the objective for this model right here. Then the coefficients in the objective of the original model became the right-hand sides of our new model. Because remember, we wanted to dominate them to make sure that we can get an upper bound on the optimal objective. And if you look at the coefficients in every row of our new model, they actually come from the coefficients in the column of the original model. So the coefficients for the first row of this LP come from the first column of this LP, and so on. So we call this LP that we have just formulated the dual LP. And once we introduce the dual LP, we call the original LP the primal LP. Alright, and these two linear programs actually have a very close relationship, and we can look at this relationship and get a lot of benefits in understanding both of the problems. But first let's look at another example of formulating the dual. So here we have an LP that has 3 variables and 4 constraints, alright? And again, the motivation is how can we derive an upper bound estimate on the optimal value z star of z here. Okay, so what we'll do, we'll introduce these multipliers y1, y2, y3, y4 for the constraints of the primal LP in order to obtain the dual LP. So you see, there is one dual variable that corresponds to a primal constraint. So there is a correspondence between the constraints of the primal and variables of the dual, right? And because we are going to use the right hand sides here multiplied by yi's in order to obtain an upper bound on our objective value, since we want to minimize our upper bound to get as good of the estimate of the optimal objective as possible, we are going to write down a minimization objective, 3y1 plus 2y2, then plus 4y3 plus 2y4. And we will write the constraints that will ensure that we dominate the corresponding coefficients of each variable in the objective. So to dominate 5, the coefficient for x1, we will look at this column right here and we'll write the following constraints. So we'll have y1 plus y2 plus 2y3 plus 2y4 is greater than or equal to 5. So this corresponded to this column right here. Looking at the coefficients for x2, we will have 3y1, then we have 0 as the coefficient for y2, then negative 1 for y3, so minus y3, and then plus 3y4 is greater than or equal to 5 again. And finally, for x3, we'll look at this column here and we want to dominate the coefficient for x3 in the objective, so we'll have y1 plus 3y2 plus 2y3 and then minus y4 is greater than or equal to 3, and we have y1, y2, y3, y4 are all non-negative. Alright, so if you look at these two problems, the number of variables in the dual problem is equal to the number of constraints in the primal problem, and the other way around, the number of constraints in the dual problem is equal to the number of variables in the primal problem, because we had a constraint for every column here, right? So then we had a maximization objective in the primal, we'll have a minimization in the dual, and we had the less than or equal to constraints in the primal, and now greater than or equal to constraints in the dual. So this is the so-called canonical form of LP. With maximization in the canonical form, we have less than or equal to inequalities, and with minimization, we have the greater than or equal to inequalities. And we see that if you write the primal in the canonical form, then we'll obtain the dual in the canonical form, right? So maximization problem with less than or equal to constraints as a primal yields a minimization problem with greater than or equal to constraints for the dual. Once again, what we have done here, we multiplied every constraint in the primal problem by a dual variable that we introduce, right? So then we obtain the following coefficient for x1 in the left-hand side of the combined constraints after we add up the results. So we have the coefficient for x1 is given by y1 plus y2 plus 2y3 plus 2y4 and so on, right? And when we sum up all of these inequalities, because all the multipliers are greater than or equal to 0, the sign of the inequality will be preserved, and we obtain the following upper bound on the sum of all of these terms here. So then, if we ensure that this coefficient for x1 is at least as large as the coefficient for x1 in the objective, meaning that it is greater than or equal to 5, then the coefficient for x2 is at least as large as the coefficient for x2 in the objective, greater than or equal to 5 again, and the coefficient for x3 is at least as large as the coefficient for x3 in the objective. Then this will ensure that this sum here is going to dominate the objective z, so we can say that z is then less than or equal to this left-hand side here of the combined constraint, which in its turn is less than or equal to the right-hand side of the combined constraint. And then what we're going to do, we're going to minimize this right-hand side in order to obtain as tight of an upper bound on z as possible. And of course, we'll minimize this objective subject to these three constraints here, right? We obtain this dual LP that we have just written down. All right. So, and as we said, we are going to call the original LP the primal LP. Okay. So looking again at the primal and dual together on the same slide, we can see the close relation that we already pointed out. So the coefficients from the objective of the primal appear in the right-hand side of the dual. Then the right-hand sides of the primal appear as the coefficients of the objective in the dual. And you have maximization objective in the primal, minimization in the dual, less than or equal to constraints in the primal, greater than or equal to constraints in the dual. And essentially, if you write these problems down in the matrix form, so for the primal we had maximize C transposed X subject to AX is less than or equal to B. So if these are the notations that we use, so essentially denoting the matrix for the constraints by A, the coefficients in the objective by C, and the right-hand side by B, we obtain this formulation in the matrix form. Then the formulation for the dual is gonna be minimize, this right-hand side now appears in the objective here, so it's gonna be B transposed times Y, right? Subject to, and we had the matrix here which was a 4 by 3 matrix for the primal problem, and for the dual problem we essentially use the columns of the primal as the rows of the dual. So we essentially transpose this matrix A, so it's gonna be A transposed times Y is greater than or equal to, and in the right hand side here we have now the vector C of the coefficients that we had in the objective of the primal problem is greater than or equal to C, and then Y's are greater than or equal to 0. Alright, so we can see that essentially in order to obtain the dual problem, we transposed the primal problem. And again, notice how the right-hand side vector of the primal problem appears as the objective coefficient vector of the dual problem, and the other way around. The objective coefficient vector of the primal problem is the right-hand side vector of the dual problem. And we also have the one-to-one correspondence between the constraints of the primal problem and the variables of the dual problem, and the other way around. The variables of the primal problem and the constraints of the dual problem. So now we know how to formulate a dual of a maximization problem in a canonical form. So at this point you should practice by writing down an arbitrary maximization problem in a canonical form, meaning that you have only less than or equal to constraints, and write down its dual.